In the last video we used a bitwise operator in the tic-tac-toe game to invert a Boolean. So say we had a value like this and we wanted to toggle between true and false. In the game it was between player 1 and player 2. You could do if is true, which is a bit of a, let's rename that, just call it A so it's not confusing. So if A is true, then A is false, else A is true. And the equivalent of that, using a bitwise XOR operator, was to simply do A and XOR it with true. And I mentioned that this simply inverts A, so if it's true it becomes false, if it's false it becomes true. It's a neat little trick. You can also, funnily enough, you can just do A is not A. I just tend to use the XOR just because it looks cooler. So there's quite a few uses of bitwise operators, and I said I'd explain them in the next video, so that's what we're going to do. So all bitwise operators work on binary, on a single bit, hence the name bitwise. So you don't work in bits in C#. It's very rare that you do. You work in bytes. So you know the lowest thing you can typically make is a byte. So it can be 1, 2, should go up to 7, I believe. 8-bit. So, oh sorry, yeah, 8-bit obviously. So if we did 8 bits in the calculator, you can see here I've switched to programmer mode, and then click this little dot, which is the bit toggling keypad. You can see there's 8 bits. So this will show us what we can get up to 255, not up to 8. I was thinking of bits. So this can be up to 255 and any more and it complains. So when you're working with binary, you're not working with like a byte here, you're working with 8 bits as it states, and that means 8 individual 1 and 0s. So you can't create a bit, there's no way to just create a bit. You have to work with your variables, but you manipulate the bits inside of this variable. So binary is effectively, as I'm sure most of you know, is just a 0 and a 1. So a binary is this, it's the 0 or the 1, and that's all binary is. It simply means yes or no, true or false. It's a very singular thing. So that's all there really is to cover with binary. You just have to bear in mind that bitwise operators work on each individual bit of your variable. They don't work on the whole variable, they work on each individual bit. And there are 4 types in C#. So you've got the AND, the OR, the XOR, and the NOT. So these are sort of helpful names I've given them to help you think of them. The AND is both, the OR is either, the XOR, you can either think, it stands for exclusive OR, but if you just think of it as different, and the NOT is inverting. So we'll get straight into this. Let's first do a variable, and let's give it a value 25. Let's keep this similar to a table I've written. So let's do 25 and say 7. Now, result equals A and B. Oh. And let's write that to the output window. Let's press F5 to run this and let's see what the result is. At first we might have to format this value so we can see it in binary. Helps if we actually tell the console to stop. So result shows 1. Now this is displaying decimal. We can use this helper, convert dot to string. You pass in a byte in this case, which is fine for what we're doing. We're never going to work above 255 in this example. And then you can cast it to base, so binary is base 2. So if we do this, we get the result 1. So we want this to be, because we're going to be working on a byte, which is 8 bits, we want to pad this out to always be 8 digits, so it shows us similar to the calculator. It shows these 8 bits. We've got 1, like that, you really wanted to see 0, 0, 0, 0, 0, 0, 0, 1. So it's always the same length. So we'll simply pad this string out. So I think it's string.pad, or do you just do it afterwards? Not pad. There we go. So we want to pad the left hand side. Total width wants to be 8. The character wants to be a 0. So anything that's not got a value is a 0. And there we go. We have like a nice result of what the result of the binary operation is. So let's just improve this slightly more. Let's remove that. Copy and paste. We want to output A, then B, and then we want to output the operation we're going to do, and in this case it's an AND, so it'd be an AND. And I'm not sure how this is going to look. Let's have a look. So that looks okay. So you can see that and that, but then it's a bit too spaced out. So let's move the AND to up here. And let's change this just to some lines. And there we go. You can see a nicer a grid, so you can see down. So this first one is the binary of A, which is the number 25. So in the calculator, we put 25 in as a decimal. And then we look at the bits. You can see here it's 1, 0, 0, 1, 1. And there you go, 1, 0, 0, 1, 1. Now in binary, because it's a 0 and 1, when you construct your data, so in this case a byte or an integer, the first part is 0 or 1, so this is 0 or 1, and you'll see this happening. If you move to the next bit, you'll see it's 2, so it's 0 or 2. The next bit 0 or 4, the next bit 0 or 8. So the way binary works is you double every time. So this is 1, this is 2, this is 4, this is 8, this is 16, 32. You get the gist. 64, 128, 256. So when you move along these bits, you make 25 by putting 1, then you don't put a 2, you don't put a 4, you put an 8 and 16. So 16 plus 8 plus 1. So you do the 16 plus the 8 plus the 1. And you'll realise that effectively in binary any number is possible because you've started with the least possible number here in terms of whole numbers. So it's a 0 or 1. The next one's double, so it's a 2. So anything in between that, you can get 1, 2, or 3. You move up to the next one, 4. You get 4, then you can go back 1 to 5, or you can go up 1 to 6, or you can go all to 7. So you can see that through binary any number is possible. So this number 25 displays as bits like this. Number 7 is the first 3, 4, 2, and 1. And then we're going to AND the 2, and you can see here the reason we got the answer 1, and I've done a little truth table in Word. So the AND operator, A and B, and the result per bit, so every bit. So you can see the AND, as it states, will only be true if both values are 1. So hence the name AND, both. So you can see here 1 and 0 are not the same, 1 and 0 are not the same, 0 and 1 is not the same. The only ones that are the same is this 1 and 1, so hence the output simply becomes 1 there. That's the only pair of bits that match. And that's the reason that 25 and 7 become 1 as an answer. So that's what the AND is doing. It's comparing the bits of these two variables, and then the result is the binary of where both bits are the same. So we can change this to say 25 and 24. Press F5. And you can see there these two bits are now the same, which is the 16 and the 8. And then the 1 on the 25 is different, so the answer is going to be 24. So there's the AND in sort of how it works. You'll see how they're used later on. So that's the AND. Now let's change this to OR and change the output to show that we're doing OR. And you can see now OR works when either one of them are 1. So if we just jump back to the Word document, the OR, so that's a 1, that's a 1, both are 1. So long as one or the other, hence the name again, OR, one or the other has got a 1, the results are 1. So the only time that it's not 1 is when both are 0. So it's sort of the exact opposite of the AND, where the only time AND's true is when both are 1. The only time when OR's true is when both are 0. Sorry, when OR's false. So you can see the results there, 0, 0, 0, 1 or 0, 1, 1, 1. You can see how those two work. And again, just think of this as if there's either one of them is true, then the output's also true. So you can see, because they've got a 1 there, and there's 1 here, even though the other one's 0, the one's there, the output's now 25. So the output stayed the same. You can do an XOR, which is an exclusive OR, which we'll take a look at this first to explain. So exclusive OR is making sure they're different. So that's why I give it the name different. So if they're both the same, that means 1s or 0s, the result's actually going to be 0, false. It's only true when the different values. So basically when they're 0, 1 or 1 and 0. So let's run an exclusive OR. And you can see now the answer is 1 again, because the only time they're different is here. They're the same otherwise. So let's just change this down to, say, 7 again. And now you can see the result. So this one's different, this one's different, this one's different, this one's different. That's the same. So you get this new number, which if you count from the left, it's 1, which isn't on. So it's 2 plus 4, which is 6, plus 8, which is 14, plus 16, which is 30, I believe. Trying to do calculation in my head while recording a video. Yep. So the result is 30. So by exclusive ORing 25 and 7, you get 30. So again, just keep focusing on it's always operating on these bits. That's all that's happening. That's all that goes on with these bitwise operators. We'll come again to how these are useful shortly. Now let's do a NOT, which is the tilde. Oh, sorry, you can't do a NOT on 2 values. Basically, a NOT is just inverting a value. So let's just invert 25. So you're going to invert 25. We'll comment out this because we're not using B. And oop, what's going on there? That's interesting. What did we do? Okay, I think this to string has gone strange there. Let's have a look at the result. So the result is, I know why, because this is an integer. We need to cast this to a byte. We could have just cast this result as a byte, to be honest. Not put it into byte. Okay. So we're just forcing these values to become 8 bits. By default, as we mentioned in one of the very early videos, when you just type a value, it defaults to a 32-bit integer. So then the result had 32 bits, and when we did this convert string, which should only work on bytes, it was getting confused basically. So this byte that it was expecting actually received an integer, and it went all strange and padded out too far. So this should fix that issue. We should be able to see. There we go. So you can see the NOT or the invert. If it's a 0, it's a 1. If it's a 1, it's a 0. So you flip around the bits. And what that means for a number is, if we copy this into the calculator, 0, 0, 1, 1, 1. So the NOT of 25 is 230. And you'll see the interesting thing here, because we're not in a byte, we're inverting effectively to get the inverted value in a similar way. It's the maximum value of the variable, so a byte is 255, and then it's minus the value 25, and that gets you the inverted. So the inverted of say 122 would be 255 minus 122. So you should get 133, which looks like this. So we should get 1 0 0 0 0 1 0 1, and you can see that's what we get. So the not is like an invert. We'll quickly jump onto bitwise shifting, which is simple enough again, and then we'll get onto these usages. So to shift bits, it simply means, again, if you look at the calculator, if we're to shift left, and I think there's a function in here to do that. Here we go, left shift. You can see the binary here, so you can still see the numbers here. We shift to the left, it literally moves all these over to the left. So that one disappears, that goes. These 4 zeros all shift that way. This one jumps to there, this 0 jumps to there, this 0 jumps to there. So it's easy to see if we just put the value 1 in first. So you can see the binary 1, and we shift it left. And you can see that's not really working as expected. I think this calculator just doesn't do it as I'm expecting, or maybe I'm not using the calculator right, but you shift left 1 and it jumps 1. There we go, just press enter instead of keep clicking. So you can see each time you're shifting left, it's moving the values to the left. You shift to the right, and okay, let's shift that to the right. Yeah, well, I'm not sure how this calculator does this, but effectively shifting to the right obviously shifts that to there. And you can see what it does is divide the number by 2. So as you're going down, 32, 16, 8, 4, 2, 1. So it couldn't be any simpler. When you bit shift left or right, it physically just moves all the bits left or right. So if you've got 1, 1 and you shift, then these are both going to move that way, and that becomes 1, 1, and then 1, 1 like that. So that's all it's doing to the bits. So let's just see that in action anyway, just to show you. So let's just change this back to, say, and. Move that down. In fact, let's just move that right to the bottom of the program. And now let's shift some values. So let's shift C. Let's make a new value. Still do 25 for now, so you can see the values. And we're going to shift C. I'm going to shift it by 1 position. And I'm probably going to have to cast this back to a byte again. So we're shifting left, and you can also specify then the number of how many movements, basically how far to the left you go. So we're going to go 1 at a time. So then that's going to become, let's output C, and the result is going to be, so we're just going to shift this by 1 to the left. Now we need a new line here to there we go. So it's this part here. So you can see there's the number 25. We shift it to the left once. You can see that 1 has moved to there, the 0 has moved to there, that's moved to there, the 1's moved to there. So you can see what's happening. So if we shift it to 3 times, we should end up with 1, 1, 0, 0, 1, 0, 0, 0. So shift it 3 times. You can see we're right on the edge now. So what happens when we shift out? So we now go past this point. What I believe should happen is, effectively, when you bring stuff in from the right or the left, when you bring in data in that obviously doesn't exist, it just brings in zeros. So you can see when we shifted this left, there's nothing here to the left, so it brings in a 0. Similarly, when you go right, it should bring in a 0. And also when these go off the end, they simply disappear. So let's just test that out. And there you see, you basically just lost the value, it's just disappeared. Now there is a thing, I'm not sure what it's called, like the term and the name for what it's called, but effectively I believe it's like bit rotation or overflow bit. And sometimes you can have if this one goes over, instead of just going over, it rotates around and comes back to the start. So it's sort of like when you shift this, say, to the right one, and this goes off here, instead of just disappearing, instead of bringing in 0, you're constantly just rotating the bits in sort of a circle. So this one ends up being over here, and then everything pushes down, and it's like a rotating circle. I only use that when I do hardware. I don't use it when I do C#, I never have. And to be honest, I'm not even sure what you set up for do that. It's a simple case of Googling to figure out, but I've never used it. I never required a need for it in C#. It's a lot more on ARM processors and assembly code that when I do that type of code, that's when you use sort of rotating bits for some advanced math operations. But in general, when you're shifting left and right, simply think of the data that's being pulled in that doesn't exist as a 0, and the bits move across, left or right, and that's all there is to it. You move left, you're effectively multiplying the number by 2. You move right, you're dividing the number by 2. So it's sort of a handy way of multiplication, I guess. So that's really all there is to the bitwise operators. So you can just keep going over this and having to play with this sort of example code to get yourself familiar with what's happening with these statements. And then we'll just now go over a few useful uses of bitwise operators. It's hard to think of examples. I've had a quick think and I can show you a few. One is to toggle a Boolean, which we've done. So that's where we have var d equals true. And now, instead of using an if and an else statement, to change that to the opposite value, you could do d to exclusive OR it with true. So you can do a not on a bit, which we've seen, because we did it up here on a byte. It appears you can't do it on a Boolean. I use this exclusive OR, which is the opposite way of doing it. So an exclusive OR means if they're different, it then becomes 1. If they're the same, it becomes 0. So the reason this works is if you think of D as your true, you're exclusive ORing with true. So they're both true. So if they're both true, it becomes false. Then when this is false, you're now doing an exclusive OR with a false and a true. Now a false and a true becomes a 1, so the false becomes true. So effectively you're jumping between these two logical possibilities. Because we're always controlling B. B is always 1. So we get rid of these because B is never 0. We're always passing true. So you're flipping between then these two values of true or false, and when it's 0 it's 1, when it's 1 it's 0. So it's a cool little trick to basically toggle, a Boolean between true and false, which you do a lot in code when you want to keep track of a certain state or a certain position of something, and you just like the tic-tac-toe game going between player 1 and 2. So that's a way to invert Booleans. So then you got Enum Flags. Now you don't need enums for this, but again it's the most common usage. So when you're trying to store data, and again it usually comes into play more in embedded electronics and hardware when you're really limited on data, and every bit is crucial. You've got to write some software and you've only got 8 kilobytes, so 8,000 bytes of data in the whole program to do everything you need. You don't want to waste, say, an integer of 32 bits to store a true or false value, or if something's only got two values, two possible values, 0 or 1, you want to use a single bit. And because again you have to work in, computers work in 8-bit, 16-bit, 32-bit, hence 32-bit architecture and 64-bit in terms of processors and things. That's talking about the number of bits in a piece of information. So if we work in 8 bits, you can see here on the binary you can store 1, 2, 3, 4, 5, 6, 7, 8 different possibilities of value in a single byte, which is 8 bits. So you can independently store a true or a false for 8 different values. So say you wanted, let's just create an enum, and let's think of something between, what could we have, values. Can't think of anything off the top of my head. Let's just give it some values. Let's just give it some colours. We won't call it colours, we'll just leave it to some values. And this could be, I don't know, a list of colours that you like. And you're not limited to one, so you can pick any of these. Red is going to be 0. Well, actually, no, red will be 1. We'll leave the 0 as nothing. And then you could have, say, blue is 2. And what we're going to do, you'll notice here now, each colour is going to be, one colour is going to be this value, 1. The next is going to be 2. The next is going to be 4. The next is going to be 8. And you'll see the reason why in a minute. So, green equals 4. Black equals 8. White equals 16. Orange equals 32. And we can go to 128. Yellow equals 64. Pink equals 128. And I think we can... 128 is the maximum. So you can see here we've got 1, 2, 3, 4, 5, 6, 7, 8 possible values as an enumerator. Now we want to store... We're going to ask the user... We're not going to, but you can. You know, ask the user what are the favourite colours out of these. Which colours do they like? So they might select all. They might select 1. They might select 2. They might select none. We can store all those choices in a single byte. So instead of having an array of do they like pink, yes or no, do they like yellow, yes or no, do they like orange, yes or no, and having 8 bytes, which is then going to take up 8 times this, so you're going to end up taking up 64 bits of data. We're going to take up 1. So to do Enum Flags, you can then do create the variable some, well, you can just use var. Some vals equals some values. So let's choose blue. Now we can output this again. So let's just output the value down here. Let's get rid of these for now. Now we know what happens here. So we're going to output some vals and because it's an enum, we want to cast it to an integer, well, to a byte in this case. It doesn't really matter which, we don't go over a byte. So we're just simply going to display what some vals is, which is blue. So it should display 2 as binary, which should show as 0, 1. So there you go, you can see what blue is with 0, 1. So we're this. Now it gets interesting when we can do bitwise operators on enumerators. So we can do or some values dot white. And what this is done, if it's ORed the 2 binary values. So blue is this one, white is 16. So here. So when we've ORed them together, the result is now this, because you're toggling the OR, as you know from the previous example just. White is this, blue is this, and ORing the 2 together becomes this, because when you look at the OR, so long as either one is on, then the output's on. So you effectively added them together almost. You can almost think of this as sort of adding the values together, so blue and white. Now if white was, say, this, if white was 3 instead of 16, then when we come to try and reverse this value and re-extract if they've selected blue or white, you wouldn't know, because if they selected only white, it's got the same bit as blue. So the importance is when you're doing flags, if you will, these enum flags, is that each value that you want to keep separate has to be double of the, each value. They've got to be at their own bit, a single bit, or even if they're not a single bit, they can't interfere. So you could have blue as being these 2 bits and white as being these other 2. So long as the bits never collide, you can do these OR values. So if we OR blue and white, and let's just run that and see, you can see we've got blue there of 2 and white of 16. So from that value now, if you receive this value, which right now is some value, so let's just cast it straight to a byte. And let's say this value was passed in, or you've loaded it from a file, or you got it from somewhere. This is now just a byte. So if we run this code, you can see now it's just, let's get rid of the hexadecimal display. It's the decimal number 18. That's all we know about this sum value is 18. So we need to now know, well, what values have they selected? So in order to re-extract the enumerators from this combined value, you have to check each time. So if we want to know if they've selected blue, so we can do if and then some value, and we want to do some value and some values dot blue. And if both of them, now you can just do in this case is greater than 0, and we'll have to cast that to a byte because that one's also a byte. Boolean? We haven't got a Boolean. What's going on here? Just got to group them, maybe. There we go. So if we do the result, which is this combined value, and blue is greater than 0, or if you want to be more explicit in case it might not be 0, you can do is equal to the value. So if you do the, I have to keep casting to a byte everywhere. This is the value we've been given in, and we simply do an and the value we want is equal to the value we want, then we know they've selected the value. So all we're doing there is we're taking this value, which is 16 and 2, in terms of these positions. So we've got the number 18, but we've got the number 16 flag and the number 2. We're doing of that value and the blue, which is 2. So then we're doing if 0, 1, and then all zeros, and this number, and we know from the truth table that and will only come out 1 when both are 1. So in this case, because we've passed in only blue, and we're anding, we haven't passed in this. So we're now going to and this value and this value. And because the only one that stays the same is this bit gets wiped out. So the white disappears. So the result is going to now be effectively blue. It's going to be that exact value because we're only passing in the exact value. So the only output that could possibly happen is either everything's off or everything inside the blue value is on. That's the only possible results because we've anded. So there's no way to give outputs of like these digits that aren't in blue because the and won't allow that because they have to both be 1. So the result is either going to be not blue or blue. Effectively, you've turned it into a Boolean statement, a true or false. So this is how it looks when you do it. It's if the value and what we're expecting to be blue is blue, it means that blue is contained within this value. There might be other values, and there is because we've got white, but this is how you'd then check for if it's blue. So then we could do console.writeLine. Blue was included. And we could also do the same, copy and paste, change it to white. And if we run this, we should get blue was included, white was included. Oop, if I change the text, it would. So you can see there, we've extracted from that piece of information whether they've selected blue or white. We remove the white. We run, only blue was included. So you can see again, you can study this and look over it and go through it multiple times, but this is effectively what you do. You do the value that you've been given, you and it with the expected value, and then you check that that result is the expected value. So these are always the same, this check, and this check's always the same. You simply input the value, and it, and then compare it with the value you expect. And that's how you compact values into a single piece of information. You keep it nice and compact. It's good for options in code. As we mentioned, you might have simple yes or no's, on or off, whether they've got an unlocked version or whether they've got certain options, or things where you want to compact the information. They're not massively used, but it's good to know how they're used and why. So that's enumerator flags. the last thing we'll go over, there's many more uses, but they get complicated, and again, it's something you can research or we'll go over in the advanced videos when we get around to those. The last thing we'll go over is masking. So a useful feature of masking, which is similar to what we've done here. In fact, we've basically done masking here. We've covered it. But when you mask a value, it's when you want to extract a certain piece of information. It really is this enum flag. So if we wanted to find, say you've got a binary, and there's your 8 bits. And now you've got, say, bit 3. So this bit here is the flag we're interested in. This is, say, the key. This is if the user has, say, an unlocked version of the program. And you want to find out with the value that they give you. So the value is going to be this. So this is the value, or this is the input. This is the important bit that we're after. And we want to know whether this bit is selected or not. So again, similar to this here. What you can do is you can mask out, and what that means is simply remove everything around that value in the input. So the first thing you do is you want to remove everything that's around it. So sort of clear it off like this, so that everything else is cleared and you're left with whatever's just the piece of information you're after. So you basically wipe out, regardless of value, you simply get rid of everything except what's in the mask. And then you're left with a simple value that you can then check like this if the value is the value you're after. So you can see here it's already been done with an AND. So to mask out the value, you simply pass in the value you expect, which is blue in this case, the important bit, which obviously this isn't blue in this example, it would be here. So let's say we move it down to there. So if we AND this value with blue, so we've ANDed these two together, the result would be all these get wiped out because this is always 0 and this is 0. So everything here becomes irrelevant and everything here becomes irrelevant, because this ANDing together is always going to wipe them out, because this input, the mask if you will, this is, you call this the mask I guess, because you're masking out everything except that value. Let's call this the mask. So the way that I'd look is var input equals a byte of some value dot blue. The var mask equals let's just do it as dot blue. And let's, for this case, let's change this to white for now. And then this would actually be white to somewhere over here. So it'd get wiped out either way. So your input's here, your mask is here, and you're going to AND the two together. And the result is going to be, in this case, it's going to be 0 because they're not both 1. The input didn't have it. So the result is going to be just complete 0. And you can see that by doing input and mask. And if we put a breakpoint, we've already used that value. We run this code. You can see the input is 16 from white, the mask is 2 from blue, and the result is nothing because that didn't match. So now if we change it to actually be blue, or in this case let's just OR it with blue so there's more in it. To group these together. So now this input is 18, which is this. So we've got both values. The mask is still just blue, but now because we ORed it with blue, this value's got a 1 here. So now the result is going to be the 1. It's going to be that exact value. Effectively, it's going to be the mask. It's going to be exactly the value of what the mask is. Which you can see here too. So mask is 2, R is 2. So this is exactly this. This is the same thing. And what we're doing is the mask, the thing we want to find out whether it is or not, we get here, and then we AND it with the input to clear out everything except the value that we're looking at. and then we effectively AND that result, just that value, and then we know then the output's either going to be not the value or the value. It's going to be the mask or not the mask. There's no other possibility. And that's how you do a check for whether there's a value inside the bits. So that's again, that really is all there is to bitwise operators. They can be confusing because not many programmers use them. They're a lot more used, like I say, in embedded electronics or in heavy mathematics or in graphic calculations. Not usually run-of-the-mill programming, not usually just day-to-day things. The only thing that's I use day-to-day really is this duck face Boolean, which just inverts the Boolean between true and false, and sometimes use these in things like, again, enums are the most common. So that's what they are. You can read up more and find out when they're used, but it's certainly good knowledge to have. They come in handy when you're doing certain things. Like, again, if you go back to the tic-tac-toe video, you'll see now where I used the OR, I believe I used when I was checking some value for whether or some and I was checking if the values were the same, so comparing two values. That should now make sense. And again, you can play about with the calculator, toggling bits on and off and seeing what the values are. And you can also take a screenshot of this and you can see your A, your B values and your expected results per bit. And hopefully that will be enough to get you the knowledge you need to understand bitwise operators.